afternoon and welcome to the Hydrogen Fuel Cells and Batteries Group exhibit. You're at the technical forum at the moment. I'd also like to welcome all of the people who are watching online. We have some great presentations for you this afternoon. I invite everyone who's around to please take a seat, enjoy coffee, water, or juice while we listen to the next presentation. Next up, we have the topic is selecting the best MEA for your cell design and your operation strategy. And here today to talk with us about this is Mr. Groos, who is the head of Department Fuel Cell Systems at the Fraunhofer Institute for Solar Energy Systems. So thank you so much, and I look forward to hearing this presentation.
Thank you very much. Hello together. Yes, I'm happy to talk to you and tell you something about our insights which we made during the last years at our institute. So, we are working with fuel cells since the early 1990s and offer research services to industry and research for a long time now. We are looking at the component level, doing tests on cell level, on stack level, and characterization of fuel cell systems. One example of our work you can see right behind you. There's this municipal vehicle which we, together with our partners in the project consortium, turned from a diesel engine into an electric vehicle which is powered by a fuel cell and battery. If you like, you can hear a talk tomorrow from Stefan Keller, a colleague in my department. Another example you can see at the exhibition and the booth of Baltic Fuel Cells. We developed together a new test cell for material characterization within fuel cells. So, and there will be a talk from Robert Arling on Thursday. So, the question for today and for my talk is, how do I select the MEA for my special cell design, my special stack design, and the operation strategy, the philosophy which I have in mind for the system operation. So what we can do today is that we typically work with differential cells for material selection and material analysis. This is a cell which I told you before, and you can see here. The major advantage is that it's a small active area and it's comparatively little effort to implement material, to exchange material, to get results. Cells like these are developed to analyze the material characteristics and to do that without any major influence of the bipolar plate design, of the flow field design, and no influence of the real operation strategy. So the test results will not reflect the total performance of a certain MEA in your concrete cell design. This cell is made for material evaluation. So the question to select the best MEA for your cell design will not be, at least not be easily answered with differential cells. People typical, the main reason is that in real cells you have gradients, so you introduce your gases to the inlet, the gases flow over the active area, there the reaction takes place, and so you have gradients regarding concentration, you have gradients regarding humidity, and of course you have gradients regarding the temperature profile over the active area. So what people typically do is to do their selection of an MEA supplier is that they integrate different MEAs into their real stack. It might not be a full stack as it's shown here, but a short stack. So you have large areas, you have like 10 or 20 cells, which means you need a large test bench, a powerful test bench, and you have a high consumption of gases. So it's a high effort at the end. And of course, as you have all of these cells and larger areas, you have an interaction of many processes, and the interaction of the MEA of the material together with the bipolar plate, with the cooling, with the operation strategy is really complex. So evaluation and analysis of the results is quite difficult. What we propose is our so-called along the channel test cell. This is a test cell which has small active area, so it's little effort regarding the test bench, little effort regarding the operation and consumption of gases, but you still can use your real channel land designs which you have in your stack, and you will operate this with your real operation strategy, so stoichiometry, humidification of the gases, which reflects your system operation. And with that cell, you can investigate and analyze the behavior of the material, of the component, of the MEA from inlet to outlet with your real designs and real operation strategy. Of course, this cell is not designed to do to meet the targets of a differential cell, so it's not designed to analyze the material characteristics itself. So what's it all about? Along the test cell, this is how it looks like. It's designed to study the effects of the customer designed channel land designs. What you can see here, you have the gas inlet. In this case, we have 9 channels in parallel. It's in this case straight channels, and then the gas flows from the inlet to the outlet. On this side, you see the cooling design, which is a simple cooling flow field, so that you can adjust through the flow of the cooling liquid. You can adjust the temperature profile, which you would have in the real stack. This cell is designed to have stoichiometric operation, so it reflects the real conditions which you have in your cell or in the stack and system at the end. As I said before, the active area is reduced to a minimum. In this case, it's 25 square centimeter, because this cell is made this way that we have a width of the active area of 1 centimeter, and channel length in this case is 25 centimeters. What you see is that we did a segmentation, so we have an electrical isolation in this case of 25 segments. Each segment of the active area is 1 square centimeter. You can do it, but you don't have to do this segmentation. But if you do this segmentation, you can really look at the local effects. This is done that way, that we integrate along the channel test cell into this measurement setup. We contact each segment, which gives a lot of cables, because each segment, anode and cathode, power line and sense line, so 4 cables per segment with 25 cells. You have a lot of cables. Each segment is connected to a single potentiostat. So in this case, we would use 25 potentiostats together with 25 frequency response analyzers. Then we can do impedance spectroscopy on a segment level. So we see how the development of the current, of the power, and of course the development of the impedance behaves along the channel from inlet to outlet in each segment. So with that, you can get results like this. So in this case, we wanted to look at the humidification of the membrane from gas inlet to gas outlet, and we did it that way that we adjusted the hydrogen flow. You see here a higher hydrogen flow, and then a step to a lower hydrogen flow, stack back, and so forth. And here you have the results. What is shown here is the high frequency resistance at around 3 kilohertz. And the high frequency resistance gives you a hint about the membrane humidification. And by looking at this curve, you can see how the humidification behaves along the channel together with the hydrogen flow. So with that, you can stand the membrane humidification in dependence of your operation strategy. For example, the membrane humidification over the whole channel length. Another example would be to investigate the degradation behavior within your channel land design and with different MEAs, which is then shown here. In this experiment, we did start-stop cycling. In that way that we did a gas change from air-air to air-hydrogen. So we have the air-hydrogen front, and then vice versa from air-hydrogen, so the normal operation of the fuel cell, back to air-air in this case. What you see here is the development of the cell voltage over time, and the different colors reflect the segment. So you see here in blue the inlet segment, and then in red the outlet segment. Here air situation. This is the phase of 6.5 seconds, the change where the hydrogen air front runs through the cell, and then we have the typical operation mode. What we can see is that from inlet, of course, the inlet segment sees first the hydrogen, so the voltage rises first, but what's interesting is to look at the outlet segment where we have this overshoot. Okay, another example for experiments that you can perform with these along the channel test cell. Degradation. When we do this start-stop cycling over a while, you see the performance begin of life in above. So here, begin of life current distribution, where you see air inlet on the right-hand side, hydrogen inlet on the left-hand side, and you see that you have higher currents at the air inlet, and then we come to lower current densities at the air outlet, which is more or less typical for cell designs like this with straight and parallel channels. When we look at the open circuit voltage, we see this distribution over the channel length. Again, air inlet on the right-hand side, air outlet on the left-hand side. After 500 cycles of this start-stop cycling with the gas change, we see a more or less complete different distribution. So we see degradation effects. Current distribution went far lower, so maximum current in this diagram is 850 milliamps per square centimeter. In the diagram above, it would be 1.2 milliamps per square centimeter. So we see a different distribution of the current along the channel length, and we also see that open circuit voltage went lower. Red is 900 millivolts, whereas in this case it was 930 millivolts. And we see a different distribution behavior. If you want to analyze this scientifically, and especially the porous structure of the catalyst layer, you can extract the resistance for molecular diffusion. Say it's the larger pores, which is shown here in orange. And then this really small pores, it's called Knudsen diffusion, which is shown in blue. And also In this case, after 600 start-stop cycles, we see that something has changed in the pore structure of the catalyst layer. So first of all, what is obvious is that the resistance went higher from, let's say, around 40 to, in this case, 120 from hydrogen inlet on the right on your right-hand side to a hydrogen outlet. And we saw that the part or the correspondence of molecular diffusion and also Knudsen diffusion changed. So with this test cell, you can see the local behavior or the local degradation behavior regarding to different accelerated stress tests, and you can do in-depth analysis of the, in this case, pore structure of the catalyst layer. So all together, to come to an end, with our, along the channel test cell, we see it as a good opportunity to have an easy and relatively fast result of MEA testing in customer-specific channel land designs. You can also use this concept to evaluate different channel land designs because it's more or less easy to manufacture different channel land designs and then look at the effects. And if you like to go more into detail, we can also offer a segmentation so that you can analyze the local effects from inlet to outlet of the cell. With this, I would like to come to an end and would like to invite you to listen to the talks of my colleagues, Stefan Keller tomorrow, about this municipal vehicle, and Robert Arling about the other concept of differential test cells on Thursday. And of course, you are heartily invited to visit us at our booth. It's right over there, C58, and enjoy a good cup of Freiburg roasted coffee together with Freiburg chocolate. Thank you very much.
And thank you very much, Mr. Groos. At this point, if there's any questions from the floor, I will bring the microphone down so that we can all hear your questions. No need to be shy, of course. This is a great opportunity to speak with Mr. Groos. But if there are no questions at this time, like you said, yeah? Okay, great. I'll be right over.
Yeah, my name is Jason, and I would like to have just asked why should the structure change of...
Could you please put the micro? It's really hard to understand.
Yeah, sorry. Why should the mass transport change? Is it due to the structure or the functional group that might have changed on the surface of the catalyst layer?
You refer to this experiment with the start-stop cycling. We did a gas exchange, so you have the air-hydrogen front which runs through the cell. And it's well known that with the air-hydrogen front you get very high potentials which lead to the conversion of the carbon to carbon dioxide. So you lose carbon dioxide, which might lead, and we are convinced that it leads to the fact that the pore structure changes. The pores result from the carbon structure that you have as carbon support. If you lose the carbon support, you will change the pore structure. And that's the effect that you can see if you evaluate Knudsen diffusion and molecular diffusion.
Thank you very much.
You're welcome.
Great, and thank you once again. And of course, you can go visit him at his booth for chocolate and coffee. So head on over to booth C58. Thank you so much for your time.
Thank you. Thank you.
At this point, I'd like to invite all of you to stick around. If you guys are standing at the back, there's plenty of space at the front. Feel free to come grab a seat, enjoy a coffee, juice, or water while we wait for our next presentation, which will begin in about 1 minute's time. Our next presentation will be on EFOI fuel cells, a flexible and cost-efficient off-grid power supply for mission-critical applications. So we'll be with you in just 1 moment.